So the yesterday's class we have discussed it, right? So what is meant by this Cauchy's integral formula, right? What it says is, suppose complex integration. The complex integration, we learned Cauchy's theorem and then Cauchy's integral theorem also, right? Integral formula. What it says is, suppose if f of z is analytic, then integral f of z by z minus a dz. This is equal to 2 pi I times of f of a. Here f of z is analytic. So this is Cauchy's integral formula. Now actually if I bring this to here, 1 by 2 pi I times of integral f of z by z minus a to dz. This is equal to f of a. Now this is what we call as Cauchy's integral formula. Cauchy's integral formula. Now in this, right, suppose if there is a function integral 1 by f of z divided by z minus a whole square, if you want to find out, then how do you find out? So for that, what we will be doing is, we will just take a derivative of this function with respect to a, not with respect to z. We are taking the derivative with respect to a. Then the derivative is coming out to be f dash of a is equal to 1 by 2 pi I times of integral f of z is constant because we are taking the partial derivative with respect to a, and this is divided by z minus a whole square into minus 1. Sorry, minus into minus. So minus of this one and into minus 1. This minus will cancel out. Finally, f dash of a is equal to 1 by 2 pi I times of integral f of z dz divided by z minus a whole square. Now actually, you can notice if f of z is analytic and z minus a is nothing but z is equal to a is a singular point, and this is a simple pole. Right? So whatever is there that is making at the denominator 0, that's what we call as singular point, or sometimes we call as pole also. And this is a simple pole. This is a complex pole. Complex will mean the order is more than 1. Still the pole is at z is equal to a, but it is more powerful than this. And if you take one more derivative, that is f double dash of a is equal to, now this is 1 by 2 pi I times of integral f of z dz divided by z minus a whole square. Now it is become whole cube, and this is into minus 2 into minus 1. So this minus will cancel. This is 2 factorial divided by 2 pi I times of integral f of z dz divided by z minus a whole cube, and this is f double dash of a. Got it? So this way, if you want to find out the nth derivative of it, nth derivative of the function function f with respect to a, this is equal to n factorial divided by 2 pi I times of integral f of z by z minus a whole power n plus 1 into dz. So this is a most generic formula for the higher order poles. This is a little bit extension to the Cauchy's integral formula. Got it? Understood or not? So this is coming into picture if there is a pole, if there is a simple pole, if there is an ordered pole. So this order can be 2, 3, 4, 5 or anything like that. Now for the complex poles, you are taking simply the derivative of it. Right? So in a way, what you can do is, this is integral f of z dz divided by z minus a whole power n plus 1 is equal to 2 pi I times of n factorial into nth derivative of f with respect to a and the value at a. Got it? So this is how actually you will be finding the complex integration with the help of Cauchy's integral formula. Clear? Do you have any questions on this? So we started at this point, the base point, integral f of z by z minus a into dz is equal to 2 pi I times of f of a. This was proved in the previous class. That's what we said Cauchy's integral formula. Now if you take the derivative on either side with respect to a, then you are getting the same integral values for the complex values. My sign. So what is the confusion in sign? Here z minus a derivative if you are taking, so I think you might have confused taking the derivative here itself. So 1 by z minus a derivative with respect to a is minus 1 by z minus a whole square into the derivative of minus a is nothing but 1 minus 1. So minus minus will become plus. Here now, Nizu. So even in the nth derivative also again, this is z minus a and the derivative is always coming out to be a factor of minus. So minus into minus will always come out to be plus. That is irrespective of n, that is always positive. I note down this based on this. So this is about Cauchy's integral formula with the extension of integral formula. So if you notice this, then actually we are going to solve certain problems based on this understanding. And with that, we will be completing this complex integration part. This is one of the very, very beautiful formula, Cauchy's integral formula. Without even calculating anything, you will be able to find the value of the integration. You are not even solving the integration at all. Clear? Yeah. Marks will be given for it, obviously, right? Noted down? So, yeah, so you have to use this. This is straightforward. And this is a base application. This is what is expected to do. Noted down? Okay. Based on this understanding, we will be solving this complex integration formula. Evaluate integral z square minus z plus 1 divided by z minus 1. Divided by z minus 1 dz, where C is the circle. Mod z is equal to 1. So this is the circle. Now here, let me explain this problem. Here, mod z is equal to 1 is the region of integration. Now in this region, if you notice, this mod z is equal to 1 is nothing but a unit circle with center 0, 0. So this value is 1. So this circle is represented in the Argand's diagram as mod z is equal to 1. Right? So this is the circle. Now here, this one at the denominator, this is the pole. So z minus 1 equal to 0. It implies z is equal to 1 is the pole. Is the simple pole. And this is located on the circle z is equal to 1. So z is equal to 1 is the real point. This is the point. So this is a singular point. Now, if there is a singular point on the region of integration, this is over the contour C, where C is nothing but mod z is equal to 1. So, if there is a singular point within the region, if there is no singular point, obviously the integral value is straight away 0. But there is a singular point at z is equal to 1. And then that z is equal to 1 is within this contour C, on the circle C. So, you have to use Cauchy's integral formula. Applying Cauchy's integral formula, applying Cauchy's integral formula as the singular point is within the region. Within the region. Now here integral value is coming out to be integral z square minus z plus 1 divided by z minus 1 integral over the contour C is nothing but 2 pi I times of f of a or f of 1, because z minus a where a is 1, f of 1, where f of z is the numerator part, z square minus z plus 1. Now f of 1 is nothing but 1 minus 1 plus 1, this is 1. So this value is coming out to be 2 pi I. This is the integral value. So you can state this integral f of z by z minus a is equal to 2 pi I times of f of a. This is the integral. Got it? Any questions on this? Any questions on this? Now, great. Now, I hope you noted down. Do the same thing if this mod z is equal to 1 by 2. Find the integral value if mod z is 1 by 2. Yeah, so here the circle of integration is this one. This is the circle of integration. Now the singular point is located at this place. Now the function is analytic at every point within the region of identification of contour C. So the singular point is being outside the region of integration. It essentially means that the function is analytic within this entire region. So as per Cauchy's theorem, the integral value is coming out to be 0 because there is no singular point within that region. Clear? Note down one more. Integral over the closed contour C sin pi z square plus cos pi z square divided by z minus 1 into z minus 2. dz, where C is the circle, mod z equal to 3. Mod z equal to 3. Can you solve this integral? I'll give you 5 minutes time. You try to solve on your own. Afterwards, I am going to solve it for you. 4 pi. Yes, that's correct, Hitesh. 4 pi I. Okay, so let me solve this. See this. Here, the region of integration is mod z equal to 3, which essentially means that it is a circle of radius 3. So this value is equal to 3. A circle of radius 3. Now there are two singular points, z is equal to 1 and z is equal to 2. So z is equal to 1 is here and z is equal to 2 is here. So two singular points. 1 two singular points. Now, being two singular points, what I can do is this denominator being the poles, we have to divide into the partial fractions. That is integral over the closed contour C sin pi z square plus cos pi z square. This can be divided into partial fractions. The way we can do it is 1 by z minus 2 minus 1 by z minus 1. So this is correct, right? So z minus 1 minus of z minus 2, that is z will cancel and 1 minus of minus 2, sorry, minus 1, yeah, plus 2. So this is plus 1 divided by z minus 1 into z minus 2. Now this integration, if you want to find it out, so this is f of z for us. And this is one pole which is located at z is equal to 2. And this is one pole located at z is equal to 1. Now these two integrals, if you write it separately, sin pi z square plus cos pi z square divided by z minus 1, z minus 2 minus sin pi z square plus cos pi z square divided by z minus 1 dz. Now this dz is, so this c being mod z is equal to 3, both the points are within the circle. So both are singular points for us. Now if both are singular points, then as per Cauchy's integral formula, this value is coming out to be 2 pi I times of f of 2. So this is f of z is this one, and 2 you need to substitute here. Sin of 4 pi plus cos of 4 pi minus here 2 pi is anyway common, and this is minus of sin pi plus cos pi. This is the value. Got it? So this is 2 pi I times of sin 4 pi is 0 plus cos 4 pi is plus 1 minus this is 0 and this is minus 1. Minus of minus is plus 1. 1 plus 1 is 2. 2 times of 4. This is 4 pi I. Got it? Everybody got the answer? Yeah, great. Okay, so you can note down this and then note down one more. Note it down, everybody. So the steps are, it is straightforward. First thing is you need to identify the region. Second thing is you need to identify the poles and then make them completely simple poles and then divide them with the help of partial fractions and then apply Cauchy's integral formula on each part of the integration. That's it. These are the 3 steps that are involved in it. Clear? Okay. Note down one more. Integral over the closed contour C cos pi z divided by z square plus 1. So z square minus 1 dz around a rectangle with vertices 2 plus or minus I minus 2 plus or minus 1. So minus 2 plus or minus I dz around a rectangle with vertices Can you solve this integration? Yes, that's correct. It's 0. Everybody got the same answer? So can I proceed or you want me to solve this? Anybody wanted me to solve? This is straightforward. This z square minus 1 you can write as cos pi z divided by z plus 1 into z minus 1 to dz. This rectangle what he mentioned is this is plus 2 and this is minus 2 and this is plus I and this is minus I. This is the rectangle he is talking about, right? So this is 2 plus I, this is 2 minus I, this is minus 2 minus I, this is minus 2 plus I. So these are the 4 corners of the rectangle. Now within this region, the closed contour needs to be identified. Here if you notice, this is integral cos pi z if you keep it as it is, and this is 1 by z minus 1 minus 1 by z plus 1. think so you need to divide with 2. Yeah. So this is z plus 1 minus of z minus 1. So z will cancel. 2 will be left over. If you divide with 2, it will be balanced. Here, this is cos pi z 1 by 2 times of z minus 1 minus cos pi z divided by z plus 1 dz. Here, if you want to find out this integral, first you need to identify the location of the poles. So there are two poles, one at z is equal to 1, another at z is equal to minus 1. So being this is 2, so there is one pole here and there is one more pole here. This is at minus 1, this is at plus 1. So both the poles are within the circle, within the region of integration. Then as per Cauchy's integral formula, so this value is coming out to be, right? So 1 by 2 times of this integral value, you can put it, this is 2 pi I times of f of a. So this is f of 1 plus minus 2 pi I times of f of minus 1. That's it. So 2 pi I you can take it out, this is pi I and this is f of 1. So this cos pi minus cos of minus pi. Being cos of minus pi is equal to cos pi, these two will cancel out. This integral is coming out to be 0. Got it? Any questions on this? Any questions on this? So note down one more. Integral e power tz divided by z square plus 1 integral over the contour C, where C is the circle mod z is equal to 3. Can I solve this integration where t is the parameter here? Now try to solve this. 2 pi I times of sin t. Yeah, that's correct. Anybody got the same answer? Other than Hitesh and Kavya, anybody else? Follow the exactly similar lines what we have done in the previous problem. Now here, this is z square plus 1 can be written as e power tz divided by z plus I into z minus I dz. So integral over the closed contour C, and this is so e power tz 1 by z minus I plus 1 by z plus I, and this you can divide with 2i, the way we have done the division with respect to 2 in the previous case. Now this is I and I, 2i over the contour C, this dz. This you can solve it with the help of Cauchy's integral formula. Got it? I think you will be able to do that. So t will be there as it is. Afterwards, you can replace e power t minus e power minus t by 2i. You can replace with sin t. Solve one more integral. Integral over the contour C. Sin square z divided by z minus pi by 6. Whole cube dz, where C is the circle mod z is equal to 1. So 1 by 2 times of sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6. 1 by 2 times of sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6. 1 by 2 times of sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6. 1 by 2 times of sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6 into sin square z divided by z minus pi by 6 into sin square Can you solve this? Yeah, pi I is correct. Note down one more problem. Integral over the contour C. E power 2z divided by z plus I whole power 4. dz, where C is the circle, mod z equal to 3. Can you solve this? So what is your question, Liju? How is derivative taking? What do you mean by that? I will be doing that anyway. Anybody got the answer? 8 pi by 3, so I times of e power minus 2. Not 2i, I think it's 2. Yeah. So let me solve this. See this. Here, integral over the contour C, f of z by z minus a whole power n plus 1 is equal to 2 pi I times of d by dz of f of z. Substitute the value z is equal to a. This is how you need to find it out. Divided by n factorial. This is Cauchy's integral formula. Correct or not? Yeah. Is this understood, Liju? So, based on this, here n is 3 because 4 can be written as 3 plus 1. So, integral over the contour C e power 2z divided by z plus I whole power 3 plus 1 is equal to 2 pi I times of 3 factorial. Right? 3 factorial. And then this is d by dz of e power 2z. So this is 3, right? So 3 times actually we need to take the derivative. And then substitute z is equal to 2. So z is equal to minus I. This is how you have to do it. Got it? Now this is 2 pi I times of 3 factorial into first derivative of e power 2z is 2 times e power 2z, and the second derivative is 2 power e power 2z, and the third derivative is 2 into e power 2z. Then substitute z is equal to minus I. This is 2 pi I divided by 3 into 2 into 2 into 2 into 2 into e power minus 2i. So this 2 will cancel out, and this is 8 pi I by 3 e power minus 2i. This is correct. Got it? Sorry, I have erased it. So actually, I think I found a mistake in this. Why? Because see this, we have got f of a into 2 pi I is coming out to be integral over the contour C f of z divided by z minus a to dz. Now actually, earlier we solved the formula for this, and this is what we found that. So 2 pi I times of the nth derivative of f, and then substitute the value a, and this is equal to integral over the contour C f of z dz divided by z minus a whole power n plus 1. This is what actually we found, and this formula is correct. But the thing is, suppose I suspect that this is plus, then this is the first derivative is 2 pi I times of f dash of a is equal to integral over the contour C, and this is z plus a, derivative of it minus 1 by divided by z plus a whole square. So this is the first derivative, and then the second derivative is f double dash of a is equal to, this minus is there, and again minus 1 into minus 2 into f of z dz divided by z minus a whole cube integral. Now here if you notice, this minus 1 whole power n into 2n factorial. This is how you are going to get it, provided if this is z plus a, sorry, yeah. Got it? So this is 2 factorial for now. So 2 pi I times of f nth derivative of a minus 1 whole power n into n factorial integral f of z dz divided by z plus a whole cube. Got it or not? So maybe this might be a correction to the previous problem. If this is minus, then you can straight away do that. If it is plus, there might be a possibility that you can get this way. Here? So note down one more. Yeah, so the question actually, yeah, e power minus 2i is correct, because actually I have given z plus I whole power. So being a is equal to I, so that's why you are going to get it. So that is correct one, whatever the answer I have given. Yeah, verify Cauchy's theorem. Verify Cauchy's theorem by integrating e power iz along the boundary of the triangle with the vertices at the points one plus I minus 1 plus I minus 1 minus I. So these are the three vertices, and this will form a triangle. Now for this triangle, you need to verify the Cauchy's theorem validity. What Cauchy's theorem states is, if integral for the function e power I z, yeah, so this is that, yeah. So what is Cauchy's theorem states is e power I z dz, right? So if this function is analytic, then this integral value is coming out to be 0. Now, this is on a region where the function is analytic. Now, around the region is nothing but the boundary or the periphery of the region where you can find out the line integral value. So, that line integral value you have, or the contour integration value, you have to find it out, verify whether it is coming out to be 0 by joining the points -1 minus I, -1 plus I, +1 plus I. These are the 3 points. Can you verify that? Prove that if the Cauchy's theorem is valid or not. So, anybody got it? Anybody got it? Okay, so let me complete this. See this. So Cauchy's, so being this is an analytic function, right? So this is a polynomial if we expand, right? So this polynomial is always an analytic function. So this value is coming out to be 0. This is RHS, and the LHS will be the integral value over the closed contour joined by all the 3 different points. Now if you identify the points on the Cartesian coordinate system, these values are 1 plus I. So this is 1 and this is I. So this point is 1 plus I and this point is -1 plus I. So this is -1 plus I. So this is exactly on the same line. This is -1 plus I. And this is the third point is -1 minus I. So this is the point -1 minus I. Now if I join this triangle, this is how we are going to get it, right? So if you put it in the Cartesian equation, this value is nothing but y is equal to 1 and this value is nothing but x is equal to -1, and this equation is nothing but with a slope of this value is 1 and this height is 1. So this slope is 45 degrees or m is equal to 1. So y is equal to x is a straight line equation. Got it? Understood or not till that point? Anybody, any questions on this? Now once you understand this, so you know that z is equal to x plus iy, dz is equal to dx plus I dy, dz is equal to dx plus I dy. Now here, if you find the integral value along the line, so there are, this is A, this is B, and this is C. This is the direction of integration. Now, in the closed contour, so integral over AB plus integral over BC plus integral over CA. So this value, you need to be finding it out. And the function value is e power IZ. So this is integral over AB. If you notice, there is the value change is only along the x direction. There is no change in the y. So on this line, dy equal to 0 and y is equal to 1. The x value is getting changed there. So this value e power integral IZ dz over AB plus integral IZ dz over BC plus integral IZ dz over CA. Now this integral value, if you expand it over AB, you can write this as put x is equal to, put y is equal to 1 and dy is equal to 0 along this line. On this line, x is equal to -1 and dx equal to 0. On this line, dx is equal to dy and x is equal to y. So these are the relations that you need to use for all the 3 different lines. So I will take the first line AB, here e power IZ. So z value, x value is changing and y value is 1. So this is e power x plus I into dz is nothing but dx plus integral over BC. So over BC, x value is -1 and dx equal to 0. So e power -1 plus iy into I dy plus integral along this line. So e power x plus ix, because x is equal to y, and then dx into dx plus I dy, so dx plus I dx, so 1 plus I. Now here everything is converted in terms of x, so you need to put the x limits. X is equal to +1 to -1, so this is +1 to -1, and here everything is converted in terms of a y limit. So y is varying from +1 to -1, so this is +1 to -1, and on this limit, so everything is converted in terms of x. So x varying from -1 to +1. Got it? So this integral value you need to be finding it out. So where I missed I? I don't think I missed I. Okay. Yeah, okay. So this will become I. This will become I. This will become I. Got it? So now actually it is up to you to solve this integration. If you add it together, it will come out to be 0. So hence Cauchy's theorem is proved. Got it? Any questions on this? Any questions on this? You can note down this. So you need to understand this process. So here we have done the line integration along all the 3 different lines. Now actually within this region the function is analytic, because this is a complete function. Complete function we mean in the entire region of the xy plane the function is analytic. So wherever you take it, the integral value should come out to be 0, being there are no singular points in it. So here this line is AB, BC and CA. So AB, BC, CA. Along line AB, y value is constant and is at y is equal to 1, and x is changing, and obviously there will be dx part. Dy will be 0 because y is constant there. Similarly, along line BC, x is kept at -1 and y is continuously changing, and dx is coming out to be 0 automatically because x is kept at -1 constant. So along the third line CA, so the integral value you can find it out by replacing z is equal to x plus ix. Why? Because the line equation is x is equal to y. So dx plus I dy can be written as dx plus I dx because x is equal to y. So if you solve all the 3 different integrations and add it together, it will come out to be 0. Clear? Any questions on this? Yeah, great. Karandeep confirmed it. So it's coming out to be 0. It will come. So that's what Cauchy's theorem says. One last problem on contour integration. Integral over the contour C. F of xi is equal to integral over the contour C. This is a closed line integral. 4z square plus z plus 5 divided by z minus j dz, where C is the ellipse. Where C is the ellipse, x by 2 whole square plus y by 3 whole square is equal to 1. Find the value of A. Find the value of f of 3.5, f of I, f double dash of minus 1. F double dash of minus 1. F double dash of minus I. Can you solve this problem? So first one is 1.1 or 115 pi I is not correct. Yeah, so what Ravindra gave is correct, it is 0. Yeah. So this is a vertical ellipse. This is a vertical ellipse and this length is 3 and this is minus 3 and then this is 2 and this is minus 2. Here 3.5, f of 3.5 is nothing but the complex function value 3.5 is somewhere here. 3.5. This is outside the region. So here if xi is equal to 3.5, this point lies outside the region of integration. So the integral value is coming out to be 0 because as per Cauchy's theorem, if there is no singular point within the region of integration, there is no need to find out. It is always coming out to be 0. That is the first case. So f of 3.5 is equal to 0 as the singular points lies outside. Region of integration. Outside the region of integration. And the second point, if you notice, f of I, f of minus 1 and f of minus I. So f of I is here and f of minus 1 is here and f of minus I is here. Now all the singular points are within the region of integration, all the three cases. Got it? Now if there is a singular point, right, if there is a singular point, obviously the integral value is coming out to be integral f of xi is equal to integral over the contour C 4z square plus z plus 5 divided by z minus xi dz. This value is coming out to be 2 pi I times of f of xi because this xi is within the region of integration. So this you can replace 4 times of xi square plus xi plus 5. This is the value. So this is f of xi. So f of I you can replace with I. So this is f of I is equal to 2 pi I times of 4 times of I square is minus 1 plus I plus 5. So this is minus 4 plus 5 is 1. So 1 plus 2 pi I times of 1 plus I. So this is 2 pi I minus 2 pi. So this is one value. Similarly, you can find out f double dash of minus 1. Now if you take the derivative of xi, so the derivative of it is 2 pi I times of 4 xi square is nothing but 8 xi plus 1. And then substitute the value f dash of minus 1. I think these are two derivatives. So f double dash 2 pi I times of 8. So this is 16 pi I. That's it. So it is independent of xi value there. Got it? So this is about the contour integration. Do you have any questions on this? I have covered all the models of contour integration. Do you have any questions on this? Any questions? Anybody? Any concept which you are not very clear? Got it? So this is about contour integration. In the next class, I am going to take up Taylor's expansion and Laurent expansion, right? Or Taylor series and Laurent series. So next class I am going to take it up. So meanwhile, actually you can solve if any of the problems on this